Student just pointed out to me a very interesting fact. I suggested in the lab that you use timer 2-3 as a 32-bit timer, but I don't think the capture units can capture 32 bits. I think they can only capture 16. So the prescaler becomes now important because you have to prescale the clock so that the overflow time is going to be greater than the blade crossing time at, say, 500 hertz or 250 hertz or 500 RPM or 250 RPM. So 500 RPM, 1000 RPM is divided by 60, sounds like 16 revolutions per second or so, times 7, so it's and halve that, so it's going to be something like a few dozen milliseconds. So you need to figure out how you're going to scale what prescaler you're going to use so that timer 2 or timer 3 does not overflow at the lowest RPM you're going to use. Yes? I think I've already said that. And that is that the lowest RPM is, of course, 0, and no amount of prescaling is going to help with that. And the highest RPM, if you just hook these motors to 12 volts, they run at 3000 RPM. Those are the absolute limits. As I said on day 1 of the setup for Lab 4, might have been a week and a half ago, we are going to test step values from 500 to 1000. We're going to ask for accuracy at 500, steady state accuracy at 1000 RPM. We're going to ask you to step it and look at the transient response. And then we're going to ask you to step it back down to 500 and look at the transient response. And it is essential for your testing that you output C of t onto the oscilloscope, the control function, the control voltage that you are using, the pulse width modulated control voltage that you are using. I'll put that onto the oscilloscope or the TFT, and you have to put out the actual motor RPM versus T as a separate channel so you can compare them. So, for instance, you might find that for a certain set of parameters, C of t looks like this, and the RPM looks like this. So you need to output the control voltage and the RPM not only for grading, not only to satisfy the TA, but because it will help you debug. Do that first. Don't do it last. It's not an added feature. It is part of debugging the lab. Do you have a question? Comment, guys? Manesh, did you have a comment or a question? So everybody remember what C of t is? So it's going to be the combination of C of t is going to be calculated as a combination of some proportional gain times an error plus a differential gain times dE dt plus an integral term, an integral coefficient times the integral from zero crossing to t of e dt. So go back and look at that stuff. You're going to have to produce a control algorithm that looks like this. And for debugging, it's really useful to look at it as a waveform. Any questions? Lab 4. What happened last night? Building circuitry last night? No? So, anything obscure happen? It just like worked? Okay.
The only thing that we had to do was we had to switch back to the old TFT library from Lab 1 rather than the one from Lab 3 because of the modifications that were made to accommodate the Lab 3 things.
So you found that you had to, right, there's always pin conflict problems, and you have to resolve the pin conflicts always, yeah, but thank you. So the TFT, you found the TFT library, the original TFT library worked better. Okay. Anything else? Op amps work okay? Those are new op amps to me, so I don't have much experience with them. So what else on Lab 4?
So we're offering those two functions to the oscilloscope with an RC filter.
Yes.
Does it really matter, like, what the magnitude? Does it matter more what the magnitude looks like? Like, let's say you have, when you step it from 500,000, it's kind of, it could be either like this or like this, depending on your.
Oh, I don't care about the gain on the oscilloscope so much, or the overall gain of the system. Yeah, remember that C of t is going to be a PWM signal, and you're going to have to low-pass filter that through about 1/10 of a second low-pass filter before you go to the scope. So tau of 0.1 second or so. 0.1 is time constant is faster than the motor but slower than the PWM, so it's a good compromise. PWM maximum speed is about 1 kilohertz, and I would run it right around 1 kilohertz, not much slower. RPM calculation, you're going to have to convert the RPM to a PWM pulse and output it if you're going to put it on the oscilloscope, or you can put both of them on the TFT. What I'm interested in is the shape of these. For instance, when you step from 500 to 1,000 RPM, does the system oscillate forever? Does it approach exponentially? Does it do the optimum thing and overshoot just a little bit and then settle? So we're going to be interested in settling time and accuracy.
So for PWM, we use like a separate timer from the quick capture or the output capture timer.
Sure. Yeah, use a separate timer. Because you want to be able to set the period of the PWM fairly arbitrarily. And again, I would set it to 1 kilohertz or so. And if you set it to 1 kilohertz, then the value of the timer prescaler will tell you the resolution of the PWM. How many counts does it take to overflow? Or how many counts does one cycle encompass? So if you set the prescaler to 1 for the timer which is running the PWM, and you have a 1 millisecond PWM, that's 40,000 counts of the timer. So the resolution of the PWM is 1 part in 40,000. So almost 16 bits. And you need then to scale C of t to use that dynamic range. So there's going to be some fiddling with scale parameters here because you're going to be setting probably the scale through P, D, and I. The error is going to have some units, revolutions per second, revolutions per minute. Those are numerically different. That's going to change the numerical value of P. But you're going to have to play with that and figure out what works. Do you think you can use floating point for this? Is there enough time to use floating point? So the natural time of the calculation that you have to meet is one blade crossing through the infrared beam. It doesn't, if you calculate 10 times faster than that, it doesn't matter, because you get no new data until the next blade crossing. And I believe that there is plenty of time to do this whole calculation in floating point. Don't have to use scale fixed point, probably. I'm pretty sure you don't. Since it ran on an 8-bit microcontroller in floating point, I'm guessing it'll run on the 32-bit microcontroller in floating point just fine. So, use floating point. And then convert to integer at the last moment when you're going to output to the PWM control register.
Remember when we first talked about that, you talked about the zero crossing and how you don't want to reset something to zero?
Yeah, I wouldn't reset the integral term to 0 on a zero crossing. So remember that you can't actually control the slowing down of the motor. All you can do is, so let's say you've stepped this is the desired speed. So now the motor ramps up, it comes up to nearly a steady state. The integral term starts to accumulate, comes over the value of the desired speed. As soon as it crosses over the desired speed, the only thing you can do with this control system that we're building is turn it off. That'll slow it down as fast as anything you can do. So you turn it off, it exponentially decays back down, builds up again, turn it off. And so if you reset to 0, the integral term to 0, you're going to get a scalloping effect like this forever. If you reset to the value the system had on the step before it overshot, it'll be about right. So you might reset to 0.9 of the current integral or so, something like that, 0.8, 0.9, 0.95. Try it and see. So you could have another parameter that you throw into the control system. I think I said that you need to be able to interactively set the speed, the proportional, the integral, and the differential term. Maybe you ought to have another parameter that you can enter, the reset value for the integral in fractional terms, so that you can interactively tune it without having to recompile all the time.
Why do we need to reset the integral at all in this case? It's not winding up error.
So integrals tend to drift because of error. So I mean, if you have a bilaterally symmetric control system, if you can make the voltage negative to pull it down again, then you expect to get more like a sinusoidal oscillation across here. And you don't want to integrate it for too long. The average should be 0, but it won't be because of noise. So one parameter, say, if I'm crossing the criterion speed, I should reset because that gets rid of any accumulated noise, and I know I'm at the right speed, so the integral term should be 0, or all of the error should be 0. That makes sense? So if you program this up with a fairly small integral term and reset it to 0, you're going to hear the system go eek 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 eek. You'll hear the torque, and the torque since the PWM is running at a kilohertz, the torque pulses will be at a kilohertz, which are easily audible. So even though the motor isn't vibrating very much, you're really sensitive to a kilohertz. So you can hear the thing. You can actually tune it by ear. What else? So let's I asked last time what people wanted to hear about that would be related to their final projects that might make an interesting lecture. The one thing that had occurred to me was to talk a little bit about musical note synthesis or waveform synthesis. And if there's no more questions, that's what I'll start doing. Yes?
Something I'd like to go over at some point is setting up the PIC 32 on the whiteboard.
Set up PIC 32 on whiteboard. Okay. The other things that occur that might be fun is talking about setting up the USB internal USB circuitry, and also how to hook up the CPU to use Ethernet, which is doable. But the whiteboard implementation is sort of embarrassingly easy. It requires 2 capacitors and a power supply. That's it. It'll boot. Now, you say, well, what about programming? And we have some microchip programmers that are separate from the little microstick boards, so that you can lay those on the table next to the whiteboard, connect them with 6 wires, and program the chip. I will try and get an image from Tamid, who uses this all the time. This is how his desired way of developing. What? The programmer? No, no, that's not part. That's you're disconnecting, and it's not part of the project, right? So standalone, need standalone, and maybe some stuff on Ethernet. Okay. So several groups want to make some combination of synthesizer or some sort of musical instrument or musical device. And so I thought I'd talk a little bit about waveform synthesis. And There's a bunch of different ways of doing waveform synthesis. One is just spectral matching. That is to say, you take an instrument, you do short-time FFT on the instrument, and you watch how all of the harmonics produced by the instrument change in time. And this gets a little bit tricky. For instance, a guitar string, when it's first plucked, is going to produce a fairly loud fundamental, but an even louder second harmonic. And then sometime later, the spectrum will look like this. So the second harmonic and the third harmonic will drop off more quickly than the fundamental. So when you talk about spectral matching, what you really are asking for is not only that you match the harmonic structure, but that you match the harmonic structure as a function of time after the beginning of the note. So you need a scheme that's fairly compact mathematically, easy to do, that allows you to produce an attack and a sustain and a decay. So you have an attack, a sustain, and a decay for any one of the harmonics. And every harmonic may have a different attack time, a different sustain, or maybe no sustain, and a separate decay time. So you have to have some way of computing probably exponentials in a compact and quick way. So then the next question is, how many harmonics do you have to synthesize something with reasonable fidelity? And the answer is, it varies. But typically, you can make something that sounds vaguely guitar-like with about 5 harmonics. So you're going to need 5 or 10 harmonics, which means 5 or 10 direct digital synthesis units to do one instrument. So another way of doing synthesis is so-called FM modulation. And this is really empirical. Something wrong with the empirical, C-A-L. Because for a lot of combinations of parameters, you actually are resynthesizing at an angular frequency higher than the aliasing rate. And you're using the aliasing to make a rich, interesting sound. And so you get these just bizarre combinations. The idea here is that you're going to pick some modulating frequency, some FM modulation frequency, and then your main frequency, your main output, is going to be given by the phase of the FM modulation plus the phase increment of the... So you have a phase increment per time for the main frequency, and then you're going to add some depth parameter times the FM phase. The depth parameter is also an exponential rise and fade and fall. You're going to get a FM modulation depth which has a transient envelope, and the main sine wave will also be amplitude modulated with a exponential rise and fall, and maybe a sustain. So you get a pretty interesting, complicated, sometimes ugly, sometimes ridiculous sound out of the system for the cost of 2 direct digital synthesis units and some multiplies. So for a certain class of sounds, you can get more interesting sounds out than you can with additive synthesis, spectral matching, additive synthesis. A third technique is physical modeling. Physical modeling. You want to make a string sound? Solve the partial differential equation. And nobody's going to laugh at that? You say, how could you possibly do that in real time on a microcontroller? Well, it turns out, for certain classes of linear systems, strings, 2 guys, Karplus and Strong, figured out how to do it in 1980 on a microcontroller, running at a megahertz. So, yeah, Kevin Karplus was a faculty member here. I think he didn't get tenure, went to Stanford and invented this. But, oh well. So, but physical modeling is interesting because you now are producing a sound which is related to the real physics of the real system, and so it can sound quite realistic. And maybe no more numerically complicated than running a direct digital synthesis unit. So those are the 3 I'd like to talk about. You don't tend to impose an artificial rise-fall, attack-decay envelope on physical modeling because the system has its dynamics that are based on the physics. If you're modeling a horn and you start adding energy to it, the sound builds up naturally because you're driving a high Q resonant system with a small input. If you pluck a string in physical modeling, then you're putting a high bandwidth, almost impulse-like function onto the string, and that results in a very fast attack and an almost exponential decay. So for physical modeling, the shape of the envelope is part of the simulation itself. And there's a guy, Julius Smith, Julius O. Smith, in fact, at Stanford, who has spent his whole life modeling physical systems of various sorts for making music, and has a wonderful website on how to synthesize whatever you can think of. A piano, which is hard. Tibetan singing bowls. All right? Turns out those are 3-dimensional resonators, and so they're hard. Drum heads, which are 2-dimensional. All kinds of interesting stuff. It's fascinating reading. So where shall we start? Oh, and there's another small thing that's nice to add into some of these synthesized sounds, and that's a little bit of noise. So certain instruments make a burst of noise when they're being played, often not very loud, but well modeled by white noise. Some wind instruments make a small amount of white noise, and adding in some noise makes it more realistic. If you're physical modeling, you may catch that with the physical modeling. If you're doing FM synthesis or additive synthesis, you won't catch the noise automatically. You just have to add it in. And so it'd be nice to have a fast, compact, random noise generator. How fast is RAND? Anybody profiled that? Anybody know how RAND operates in GCC? That's a fairly obscure question. It's a multiply and an add and a modulo 32-bit. So it's pretty fast. It's actually probably fast enough for everything you want. You can, it is uniformly distributed white noise. If you want to take a uniform distribution and turn it into a Gaussian, add 3 of them, or 5 of them, or 12 of them, or however much time you have, and the output will be approximately Gaussian. Because no matter what the distribution is, if you add a bunch of them, you get a Gaussian. Right. So let's start by talking about attack and decay generation, since that's common to a couple of different techniques. So overall, what we're going to do is we're going to say that the amplitude of the synthesized note is going to have some initial value, some scale factor, times e to the minus t over the fall rate, or the fall time, times 1 minus e to the minus t over tau rise. So we're going to model the processes as exponential, although it's not unique. And so we're going to be able to produce features that look like this, or features that look like this, or features that have low amplitude but have a long rise time. This particular system does not perform well when the rise time is long compared to the fall time. We can fix that by faking it a little bit, by saying we don't cut this one in, we don't allow this to start decaying, we don't allow the system to start having a fall time for some fixed amount of time. And that makes the sustain. So we're just going to force this. The rise time rises naturally, but then just gets held for a while before the decay starts in exponentially. So we just hold this at a value of A naught. So let's abstract this slightly for as A naught is equal to envelope fall times envelope rise. And then think about how to calculate the rise and fall envelopes separately. And they're first order systems. So we could have a gigantic table of exponentials. You can't afford to do exponentials in real time because it's 7 or 8 multiplies to calculate an exponential. So what you'd really like to do, and having a table is hard because you have to parameterize the table by the fall time, and you have to keep track of absolute time. So why not just do it incrementally? What we're going to do is we're going to have a variable which is going to be some state variable, say dx dt is equal to minus kx, first order system, with a naught equal to x at t equals 0. And what we're going to do to pluck the instrument or to play the instrument is to load a value, a non-zero value, into x. So we dump some energy onto the system and let it decay away however it's going to decay. Which means we're going to solve the differential equation to produce the exponential rather than trying to read back a table of exponentials. So the handy old Euler approximation says that x at time n plus 1 minus x at time n over delta t is equal to minus k x at time n. And we can rearrange that a little bit to x n plus 1 minus xn over xn is equal to minus k delta t. Now, this is a constant. And we can rearrange it further to say that xn plus 1 is equal to xn times 1 minus k delta t. So in other words, if we know xn, all we have to do to get the next time step of the amplitude is to multiply by a constant less than 1. So the exponential calculation for either fall or rise then is reduced to 1 multiplied. So what we're going to do then is we're going to use this system once for the fall time. We're going to use a similar system again for the rise time. We're going to calculate a decaying exponential and then subtract it from 1 to make a rising exponential and multiply them together. So for every time step through the simulation or through the node generation at some constant synthesis frequency, we're going to update an exponential for the rise time. We're going to update an exponential for the fall time. We're going to multiply them together, and we're going to multiply, and then we're going to use that to set the amplitude of a sine wave or the amplitude of an FM wave. And to see how well this worked out on PIC 32, I implemented an FM system. But now the FM system has attack and decay for the FM modulation. It has attack and decay for the main sine wave. It has 2 phase accumulators, one for the main frequency, one for the FM frequency. And the whole thing takes only 5% of the CPU using 32-bit fixed point. So you can build a lot of these things if you want to make a interesting sound. I have time to show a little bit of code. Oh, XKCD, yes. My favorite comic strip, and probably most of yours too. So we go down to the links. There's a DSP link. And I haven't separated this out into different kinds of processing. So right now there's all kinds of stuff in there, from infinite impulse response filters to FM sound synthesis. And here's a summary of the math I just said, that we're going to produce a waveform which is given by some envelope for the main function times a sine wave, whose frequency is given by some base frequency F main plus an envelope for the FM times a sine wave frequency. And there's all the rearrangements I talked about to get to the compact version of the But let's go look at the code where we can see this. I added a couple of constants here, fixed point constants. I added 1 because I was tired of writing this for 1. And I wanted a sustained constant, which is going to be, which converts a number that you type into the terminal to ticks, to clock ticks. But the heart of it is very simple. There's a phase accumulator for the FM that gets incremented by the FM modulation frequency. There's a main accumulator which gets incremented by the phase of the main frequency plus the scaled FM envelope frequency, the sine wave resulting from this phase accumulation. Does that hurt? That makes sense? And to play the thing, there's some input to this, which is a play trigger that would be a push button, say, that a human would push. You increment the decay and the main for the FM and the main to their appropriate values. You initialize the attack. You set the play trigger back to 0. You zero the phase accumulator so it's phase locked. And then there's a couple other counters. And the reason for that is that the time scales are so different. You want to do the audio synthesis at 20 kilohertz, but you can't afford to calculate the very slow decay at 20 kilohertz because you don't have enough arithmetic accuracy. So what you have to do is slow down the calculation of the envelope by a factor of 256 or so, so it's going at more like 100 hertz or so. And one reason you need to do this is that many instruments have a very high mechanical Q. They store energy for a long time, so you pluck a string and you can hear it for hundreds, if not thousands, of cycles. So the system is a little bit, to use a technical term, stiff, in the sense that there's a very long time constant for the decay and a very fast time constant for the sine wave. So we're doing a modulo operation here by ANDing with FF. We're doing a modulo 256 by ANDing, cheaper than doing a divide. And doing these multiplies I talked about, calculate the exponential decay of the FM, the exponential decay of main, the attack exponential for FM and main. Then calculate the envelopes as 1 minus the attack state times the decay state. Check to see if we're actually in sustained mode and do the cheesy fix. And And then there is one more multiply that's done. And I started to write before I did this because that means you don't have to wait as long. You do more calculation while you're doing the SPI because the SPI is in hardware and runs independent of the CPU. So you can do calculations. So I did a multifix during the DAC write of taking the main sign table, multiplying it by the envelope, and then putting it into DAC data for the next loop through the code. So the synthesis is extremely easy. It's kind of, it takes a while to get all of the state variables right, but it's quite easy to set up. It'd be nice to parameterize this into a function call so you could build a bunch of them. I haven't done that yet. So I played a few of these last week, and it's an interesting sound, although it's ambiguous. To me, something that sounds like a string sounds to a student who walked in the door like a bell. All right, they're both high Q resonators, but it's an interesting but ambiguous sound that comes out of it. Does anybody think they're going to use FM sound? FM synthesis? Don't know yet? Anyways, this is written. You can play with it. There's a user interface, in a manner of speaking, in that you can set all of the parameters from the keyboard of the computer. So you can set the frequencies for the FM and main. You can hit P to play the note. You can set all of the parameters and then read them back because I couldn't keep track of them. So you can play with it, see what it sounds like. I haven't built an additive synthesizer yet for this architecture, nor have I gotten Karplus Strong algorithm running yet. I might show you some code from the 8-bit microcontroller. Much of it is the same. Some of it is different, but we'll certainly talk about some of the underlying math of the physical synthesis. Any last minute questions? Any more questions about yes?
Would it be advisable to use an external IC for any really complicated sound synthesis? So use a coprocessor of some kind to do sound synthesis. Certainly, that could be useful, particularly if you needed a big table lookup. For instance, to get the waveforms for the 64 or so English sounds you need to synthesize English, which is about probably takes up more memory than exists on this chip. You could also imagine having a coprocessor that does direct digital synthesis in hardware, which would give you lots of channels directly. In 5760 using an FPGA, you can probably do 100 channels of FM, maybe 200 channels of FM, or several dozen Karplus Strong strings. But you got a lot of bandwidth there, a lot of parallel capability. What are the questions on Lab 4?
Okay, I'll talk more about music next time.